Today, we will talk about AutoML for TinyML with the once-for-all network. My name is Song, a system professor from MIT. So training and deploying deep neural networks require many engineers. The model is difficult to tune, especially to make it efficient and compact. And the model is usually pretty large to achieve very good accuracy, and thus it requires a lot of computation and make it very difficult to be deployed on those embedded devices. Okay? So the goal of this project is to make AI more efficient with less engineering resource by AutoML and less computational resources to achieve TinyML. Okay? So that the whole pipeline will require fewer engineers and also produce smaller models and require less computation and make it more efficient to be deployed on edge devices. Okay. So the challenge is efficient inference on diverse hardware platforms. So we have a broad spectrum of hardware devices to deploy neural networks, ranging from cloud AI to mobile AI to tiny AI or the AIoT. Okay. A cloud GPU may have a very large memory, such as V100 has 32 gigabytes of memory. The computation power is teraflops per second, right? And the mobile device, like this mobile phone, the memory is roughly around 4 gigabytes, right? And the computation power is gigaflops per second. And a tiny microcontroller, the memory is less than 100 kilobytes, and the computation could be far less than millions of flops per second. So it's very difficult to have one model that can fit all devices, right? And since different hardware platforms have quite different resource constraints, and we need to customize our models for each platform to achieve the best accuracy efficiency trade-off, especially on those resource constrained edge devices. And this could be quite expensive. For example, when we have just one mobile phone, okay, when we have just one mobile device, we can just train one model, for example, MobileNet version 2. On the left-hand side, you can see the basic schedule is for this amount of iterations, which we just do forward and backward. And after 200 GPU hours, that's roughly 4 GPUs for 2 days, we can obtain a trained MobileNet. A new approach is the neural architecture search, which is pretty hot recently. It adds an outer loop to search for a couple of search episodes, right? And since the rectangle is the hard code that is really time-consuming, you have to do many forward and backwards. It's very expensive to have another for loop outside of it, like the neural architecture search does, right? If the model is great, then we just break. And since the model is usually trained on smaller data sets like CIFAR or trained with less epochs, we usually need to fine-tune or train again the architecture. So that's the second hot code, the second rectangle for post-search training iterations. We train the model again. That makes the training cost a lot larger, 40K GPU hours. And when we have diverse hardware platforms, we added another for loop outside, which make it even more expensive. Now there are 2 for loops outside the back propagation. Okay, so if you have 4 devices, then that's 160K GPU hours, and we have even more hardware devices, right? Like cloud, mobile, or tiny. This is the case for many internet companies when you have diverse product lines, both the cloud line and also the embedded product line. Even for a mobile company or a mobile app, you may have different features that require different neural nets, right? And you have support on both the new mobile phone and an old mobile phone, right? So this is actually a quite practical application scenario that many deep neural network practitioners faces these days. So this could be make it even larger since the design cost grows linearly with the number of hardware platforms. So how to solve this issue? Or recently, this could lead to a quite severe environmental problems. For example, translating the GPU hours into the CO2 emission. So the problem is the TinyML comes at the high cost of big ML, right? So TinyML is what we want to achieve at inference time. But in order to obtain or in order to search to find such a small and compact model, we have to pay a lot of computational resource to train it, to search it. Okay, we need green AI to solve the environmental problem of NAS. Last year, there's a paper from ACL covered by MIT News saying that training a single AI model, here is the evolved transformer with neural architecture search, can emit as much carbon as 5 cars in their lifetimes. So this can be quite expensive, right? Just to train a neural network, the amount of carbon footprint equal to 5 cars for their entire lifetimes. So this figure shows the common carbon footprint benchmarks. Like human life, 11,000 pounds of CO2. American life may be more less efficient, so that's 36,000 pounds of CO2. Okay, and US car entire lifetime, that's 100,000 pounds of CO2. But the evolved transformer with 230 million parameters with neural architecture search, that takes 626,000 pounds of CO2 emission, which equal to 5 cars. So this could be quite expensive. And our method, which I'll introduce later, make it 4 orders of magnitude less. So only 52 pounds of CO2 emission with the hardware-aware transformer, which is supported by our once-for-all network. So the main feature that we are proposing here using once-for-all network is decouple training and search. So on the left-hand side, that's the algorithm for conventional neural architecture search. When we have an outer loop and an inner loop, the inner loop just does the back propagation. And on top of it, we have an outer loop to search many episodes. And this can grow, the search cost grows with the number of devices. And usually after search, we have to train again. But once for all decouples training and search, where we just train the model no matter which device do you want to specialize it later. And then we have the search process. When we first, for many devices, for many search episodes, we just sample from the once for all network, just sample from it without having to retrain it. Sample from the once for all network, see the test accuracy, right? If it's good, then you just keep it. If it's not, then you just continue. You can use, we actually used evolution here to do the search. And the search is based on a subset of the training data set to prevent overfitting. Okay. And the merit of the once-for-all network is that after the search, we find a good architecture, we can directly deploy the weights without retraining. Okay, so that's the main feature of once-for-all network. And we are going to talk about how we achieve that very soon. Therefore, we cut the search cost when we are handling many devices by a large order of magnitude. So this is how the once-for-all network work. Say you have 3 different deployment scenarios: the cloud AI, the mobile AI, and the tiny AI. So for the cloud AI, you may pick a larger subnetwork from the once-for-all network. And for the mobile AI, we may take a middle size of the network since it has less computational resource. But for tiny AI, we can pick just an even smaller subnetwork. So all these 3 subnetworks are not retrained, right? They are directly selected, directly grabbed. Their weights are directly grabbed from the once-for-all network, right? And thus, we can save a lot of computational resource. We just train only once-for-all network, and then we can amortize such training cost across many deployment scenarios and many hardware devices. But this is not free lunch, right? The challenge is that how to prevent different subnetworks from interfering with each other, right? Like the large model, the middle-sized model, or the small model. How do we prevent these models from interfering with each other? And that's the key question we want to solve. And the solution here is that we proposed a progressive shrinking algorithm, okay? Progressive shrinking algorithm to support both the large model and also the small model. The high-level intuition is we want to first support large model and then support small model. And in this broad spectrum, our case can cover 10 to the 19 different subnetworks in a single once-for-all network. Right? To achieve that, we cover 4 different dimensions, different resolution, different kernel size, different depth, different width across these 4 dimensions. Okay. Directly optimizing such once-for-all network from scratch is much more challenging than training a normal neural network, given so many subnetworks to support. And we find following this training large model first and then gradually make the model smaller is better than not following such order. Since during SGD, we are using a convex optimization method to deal with the highly non-convex method. Thus, redundancy is actually preferred during the initial training dynamics. So this is the high-level overview of progressive shrinking. So we first train the full model, okay, and then we shrink the model across these 4 dimensions: resolution, kernel size, depth, and width. And after that, we jointly fine-tune both the large and the small subnetworks. We fine-tune a whole broad spectrum of subnetworks. And we repeat this process until we get a good once-for-all network. So for those who are familiar with model pruning, you may find it's roughly kind of similar. We shrink it, we prune it, but that's only in the channel dimension. We're going to talk about the relationship between progressive shrinking and pruning in later slides. Okay, so smaller subnetworks are nested in the large subnetworks. So their weights are shared. So you just train one model can contain many models. And we cast the training process of the once-for-all network as a progressive shrinking and joint fine-tuning process. So this is the connection to network pruning. Pruning shrink, for example, channel pruning only shrink the width, but here we shrink the model across 4 dimensions, including not only the number of channels, but also the depth, the resolution, and also the kernel size. Right? We can support large resolution, small resolution. If you have lots of resources, we just use a large resolution. If you have a tiny microcontroller, we can use small resolution, right? Large kernel, small kernel, similar idea. Deep model, shallower model, okay? And during the fine-tuning stage, we not just fine-tune the small network. And since we are supporting a broad spectrum of neural nets, we fine-tune both the larger subnets and also the smaller subnetworks, okay? So progressive shrinking can be thought of as a general case of network pruning. So this is the high-level idea of progressive shrinking across these 4 dimensions, including resolution, kernel size, full kernel size, and also partial kernel size. Elastic depth, full depth, and also partial depth. And also elastic width from full width to partial width, right? So this is a detailed illustration one by one. To support elastic resolution, we can randomly sample the input image size for each batch. This could be also a very good regularization. And for kernel size, we should start with 7x7 kernel, which is the largest kernel, right? And then gradually support 7x7, 5x5, and then 7x7, 5x5, and 3x3, okay? And here the smaller kernels are actually the centered weights of the larger kernel with a transformation matrix. For example, from 7x7 to 5x5, the transformation matrix has 25 weights. Different layers have different transformation matrix, but the same layer across different channels, you have the same transformation matrix. Okay, this slightly adds the accuracy. And from 5x5 to 3x3, we have a 9x9 transformation matrix that transforms the center of the 5x5 layer into the 3x3 layer. Okay. And to support the elastic depth in this example, we first train with full depth, and in this case, the depth is 4. And then we shrink the depth to support both a depth of 4 and also a depth of 3. Okay. And after that, we support even smaller depth, like depth of 2. In the meantime, we also give it equal possibility to support depth of 2, depth of 3, and also depth of 4. And finally, we support elastic width. Width can also be described as the number of channels. Okay, say for a layer, it has full channel number of full width of 4 channels. Okay, and then we sort the channel based on their importance, which is represented by the L1 norm of this channel. We sort it and reorganize that and pick the largest chunk of them to be the smaller width. So in the second round, we support both O1 and O2, which is both 4 channels and also 3 channels. And then we sort them by the importance again and reorganize the channels again. And the next iteration, we support both 2 channels, 3 channels, and 4 channels. Okay, so the idea here is to keep the most important channels when shrinking via the channel sorting. So the common feature across these 4 dimensions is that they are all elastic, right? Just like a cloud computation, just like cloud compute, right? When you have a very powerful inference hardware, we can use the full resolution, full kernel size, full depth, full width, right? And when you are running the model on a old mobile phone, for example, you have a single app that have to support both the new phones and also the old phones, right? You have an old phone, you may support smaller resolution, smaller kernel size, smaller depth, smaller width. So put it together, a progressive shrinking has 4 steps: elastic resolution, elastic kernel, elastic depth, and elastic width. We start by training a full network and gradually shrink the model across these 4 dimensions, okay? And the experiment shows that such progressive shrinking, which is shown in the green bar, has superior performance than without the progressive shrinking. Okay, so we can tell the difference across different depth with kernel size across all these subnetworks with progressive shrinking in green have about 3% or more superior performance than without progressive shrinking. Okay, so far we covered the training phase. Since we decoupled training and search, how about search? How do we do the search after we train such a once-for-all network? For each device, we have several search epochs. We just sample from the once-for-all network. And the main advantage of once-for-all network is that each individual subnetwork, you don't have to train it again. That's why I used a dashed line, or dashed rectangle for the sample from OFA. Is very cheap, very light. You don't have to train the model. You just need to run the inference to get the accuracy of the subnetwork. If the subnetwork is good, then we just stop, right? And then we can just directly deploy the subnetwork without retraining, okay? That's why I also use the dashed rectangle, showing that it's not computationally intensive, okay? So this is the beauty of decoupled training and search. No matter how many devices you want to support for specialization, you just use the same once-for-all network. Therefore, you don't have to pay a lot of computation resource for forward and backward to train the big model. And during search, we used the evolution strategy to sample the OFA to get the subnetworks. Okay. All right. So here's the result from this strategy. Okay. So we measured the performance of once-for-all network on Pixel 1 mobile phone to get the measured latency Okay, it's about 2.6 times faster than EfficientNet with the same accuracy, actually better accuracy, and 1.5 times faster than MobileNet version 3 with the same accuracy. Okay? So on the left-hand side, we can see the comparison with the EfficientNet in blue, where there are 3 EfficientNet models that you have to train 3 times. Their accuracies are 76.3, 78.8, and 79.8, right? And we have 3 models too, but we just have 1 model. We can directly derive these 3 models. Okay? You can see the highest accuracy is already over 80%, right? 80.1% top line accuracy, which is a new record for mobile phones to have such great accuracy. It's about 2.6 faster than the 79.8 top line accuracy EfficientNet. Or with the similar latency, roughly 150 milliseconds, it achieved 80.1 accuracy, top line accuracy on ImageNet compared with the 76.3% top line accuracy on ImageNet. On the right-hand side is the comparison with MobileNet version 3. So around 20 milliseconds. So by the way, this is without quantization. With quantization, the latency could be even shorter. It's about 4% higher accuracy, or with the same accuracy of 73.3%, once for all is about 1.5 times faster. And the most interesting thing is that after this progressive shrinking procedure, we find the model trained by OFA training schedule is better than you use the same architecture, okay? The neural architecture. They reinitialize them from scratch with random initialization and training from scratch. We get the green line, okay? We get the green line. So same architecture, but our model after once for all can have a higher accuracy, consistently higher accuracy than those individually trained model initialized from scratch with the same architecture. Therefore, the interesting phenomenon is it is not only the architecture that is important, right? But also the way you train it that is also important, right? So the architecture we searched is in a better Pareto optimal curve than both the EfficientNet and also the MobileNet v3, right? But that's the green line. We can do even better by using our training procedure with sharing and progressive shrinking to get the right line. And the main reason here is such weight sharing as a level of regularization. So not only each subnetwork has to function really well, but when combined with some other networks, for example, a larger kernel or a smaller resolution or a deeper model, right? When you are combined, when you are with different model capacities, you still have to function really well. This is a pretty strict constraint, and such constraint adds a regularization to this training procedure. And the second reason is during the training progressive shrinking procedure, we have the distillation from the full once-for-all network and the sub-network. And different from conventional distillation here, we have the subnetwork share the weights with the large network. So it's kind of self-distillation, okay? So that's the second reason such network perform better than training from scratch. And we also compared if we only have distillation, but without such progressive shrinking. And the result is worse than when we are having both progressive shrinking with the sharing and also the distillation. Even the larger network, right? So distillation cannot improve the accuracy of the largest network. That's the conventional case. But in our case, even the largest model, like the 80.1% top-line accuracy model, that accuracy is improved by such weight sharing and progressive shrinking. So that's the contribution cannot be achieved by distillation alone. But weight sharing really helped. Okay. So we plotted the computation and accuracy trade-off on this entire figure. So once for all sets a new state-of-the-art 80% image one-top-line accuracy under the mobile vision setting, which means it's less than 600 million max. So once for all, it's on the top left corner, which has 595 million max, achieved 80% top-line accuracy on ImageNet, which is 14 times less computation than exception with the same or even better accuracy. So mobile setting means it's what we are particularly interested in is here the capacity should be smaller than 500 or around 500 million max. So once for all, network enables fast specialization on diverse hardware platforms. So here we experimented with Samsung phones, the Google phones, the Pixel 2, the LG G8 NVIDIA GPUs, Intel Xeon CPUs, and even specialized hardware like Xilinx FPGAs. So once for all network consistently outperform the baseline, which is the MobileNet version 3, by a pretty big margin. And then MobileNet version 2, since the FPGA doesn't support MobileNet version 3 yet. And for example, on the GPU, on the bottom left corner, we can see both with 72% accuracy, ours is 72.6. Original MobileNet version 2 runs about 28 milliseconds, but the Wi-Fi runs only 12 milliseconds, which is more than 2x speed up without any change of the hardware and without change of the library, right? And for all these 6 devices, we have 6 different specialized models. But we only pay the training overhead only once, right? That's the beauty of once for all model. You can design specialized model catering for your hardware. For example, the GPU and the mobile phone have different parallelism, have different amount of SRAM, different memory bandwidth. It doesn't make sense to design just a single model for all these cases, right? And once for all network can have a single mother network and have many sub-networks that are quite different. We also tried actually even more cases. We released 50 plus, more than 50 pre-trained models on different hardware devices. Okay, and we compared with the MNASnet, the MobileNet version 2, and also the Sleepable Net as a holistic study. And once for all network showed quite consistent performance improvement. So an interesting experiment we did is once for all network for FPGA accelerators, which is a specialized hardware, right? So here we define a concept, the arithmetic intensity, and we find the once for all network achieved a higher arithmetic intensity than MobileNet V2 and MNASnet on the FPGA. So arithmetic intensity is defined as operations per byte, right? Which is basically the x-axis of the roofline model, very important in hardware architecture. So memory is expensive, computation is cheap, right? So we want to fetch 1 byte of memory and do as much of computation on top of it. So therefore, it's not memory bounded. And such once for all training procedure and search method can achieve a higher arithmetic intensity, meaning that it's less memory bounded compared with other workloads like MobileNet V2 and MNASnet, right? And therefore, it achieved a higher GOPS per second, the peak throughput, not the peak throughput, the achieved throughput compared with 57% better than the MobileNet version 2. Okay, so making it hardware aware is very important since here we use the latency as the feedback during the search process. All right, so go back to our green AI goal. So here we can achieve the CO2 emission by a large margin, right? And we can roughly have 2 methods here. One method is like on the left-hand side, like the once for all model, we can amortize the search cost across many subnetworks and many deployment scenarios. We design we train only once, and during search we no longer have to train. Thus, we can amortize this training cost. And another method is from another paper in the iClear from our group, the light transformer, to have the human-in-the-loop design, where we apply human insights of both the hardware and machine learning knowledge rather than just do brute force search. For example, in this case, we find that the conventional attention mechanism will produce this diagonal structure, as in the figure, diagonal structure of the attention map, showing that we are wasting a lot of model capacity to model those adjacent context modeling. And therefore, we just use the convolution to model the adjacent context modeling, and we use the attention-only model, the long-range modeling. So with such human-in-the-loop or human insights, we can achieve even better performance than the evolved transformer on the mobile setting, but save the number of CO2 emissions by 4 orders of magnitude. Okay. So once for all, such training procedure has a broad spectrum of applications. We applied once for all mechanism to design an efficient transformer for NLP, and also efficient video recognition for vision, and efficient 3D vision, and also efficient GAN compression. So the common feature of all these neural nets they are computationally expensive, and they are what we are interested in. Right, like training birds is super bulky, and both video and 3D vision, they are more computationally intensive than 2D, and also again the pixel-wise prediction also computationally expensive. And once for all, this progressive shrinking method give a good compression. For example, applying once for all to the hardware to the machine translation, we can get the hardware-aware transformer. We can deploy them in real time, hopefully on the edge devices. That's a goal. So once for all, applied to transformer, we can save the latency on Raspberry Pi by about 3.7 times, by about 3.7 times smaller model size and 2.9 times faster inference. And we evaluated on CPU and GPU, it's 1.6 times faster and 1.5 times faster, and 12,000 times less CO2 than the evolved transformer with respect to the training cost. Another application is for efficient video recognition. So compared with the Resonant 50 plus temporal shift module, temporal shift module is from our group published in SCCV 19 for efficient video understanding, targeting those edge devices like surveillance camera, IoT device, or the mobile phone, right? For example, detecting a person falling or passing out. It can save the computation by 7 times compared with the Resonant 50 plus TSM, or make the accuracy 3% better, but with the same amount of computation than TSM plus the mobile net version 2. And OFA can also be applied to produce efficient 3D recognition models. Efficient 3D recognition is quite important. For example, on VR and AR devices, people may have a whole backpack of computer because it's so computationally intensive. And for self-driving, since LiDAR is important sensor, self-driving has a whole trunk of GPUs to process those so many cameras, so many LiDAR data, right? So once for all, together with an efficient backbone, the PPCN can achieve 1.9 times speed up compared with the state-of-the-art Minkowski net, or with 3.6% better accuracy under the same amount of computation budget. Here, we also apply OFA to GAN to compress GANs. So for example, here is accelerating horse to zebra, the classic pixel-to-pixel model, right? Before compression, we can run it at only 12 frames per second. You can see slowly making progress. And after compression, it runs on the same piece of hardware, the Jetson Xavier mobile GPU. It runs much faster at 40 frames per second with even lower and better FID. Okay, 3.3 times speed up. On the right-hand side, we evaluated the model on a broad spectrum of hardware devices, including the CPU, GPU, mobile CPU, on cycle GAN, pixel to pixel, and also Gao GAN, right? The flop reduction ranges from 8 times to 21 times. The speed up ranges from 1.7 times to 18.5 times, okay? So in summary, Voice-for-All network has a broad applications, and the key idea is the progressive shrinking idea. Train from large model and then gradually shrink. Not only shrink one dimension, but also shrink many dimensions. Here we have 4 dimensions, okay? And it will efficiently produce many subnetworks for efficient and specialized model design for diverse hardware platforms, okay? And another key idea is decouple training and search. Since training is very computationally expensive, no matter how many scenarios you wanna deploy, you just train only once, and you search many times. Decouple training and search. Okay. And with this technique, we received the first place in the third Low Power Computer Vision Challenge DSP track at CV19, surpassed those human designs, and also the first place in the fourth Low Power Computer Vision Challenge at the NeurIPS 19 early 2020. Actually, after NeurIPS 19, both the classification and detection track, we surpassed those human performance. Okay. And to build a community, we have released more than 50 different pre-trained Voice-for-All networks on diverse hardware platforms, including CPU, GPU, FPGA, and DSP. Okay, and you can easily get this specialized subnetwork using just one line of code by taking advantage of our pre-trained Voice-for-All model. We also released the training code. You're very welcome to contribute. If you have a new device you want to specialize it for, like the TPU or another device or another mobile phone, right? So that you can design those pre-trained, and you can use your own design space to follow this progressive shrinking, decoupling, training, and search method to design your own Voice-for-All model and also the specialized network. Okay, and the project page can be found at the bottom. So here are a complete reference of our line of work covering model compression and neural architecture search. And the applications ranges from computer vision to natural language processing to make it more efficient for those mobile and edge devices. Okay, and finally we have the hardware design EDA to support those sparse and compressed models. So this is the full stack design covering both the applications, the tools such as the Voice-for-All method or the proxyless NAS. By the way, I highly recommend to check out proxyless NAS as well, which is an efficient neural architecture search method taking the hardware feedback into the search loop, also very efficient, which has been adopted by the AutoGluon from AWS and also the integrated into the Facebook PyTorch Hub. Okay. All right, that's all for my presentation. And our big dream is to make AI more efficient with the tiny computational resources. Okay, that's the TinyML, and also tiny human resources. That's the AutoML. Okay, so AutoML for TinyML. Finally, I give my sincere thanks to my many hardworking students, very productive students. And also you're welcome to check out our GitHub. We have open sourced or will open source pretty much all the projects that we have published so far, including every paper that we covered today. And also subscribe to our YouTube channel where we released a lot of demos and also a lot of talks. Okay, thank you everyone.